Okay. I am Robert D. Giovanni. I teach pretty much everything we offer here, and I was told this morning that Stephen Gonzalez would not be here if anyone wanted to sub Cal 2. And no one ever really wants to sub because you got to walk into just unknown territory, but Cal 2 is something that you can't miss a day, you know? Like, and I'm not saying Stephen, I'm just saying I don't want you all to fall back another day. So if I can come in here and help you out in any way, I'm going to try to. So the way I'm going to do this is the way I do all my classes. I stand up here. I'm going to be projecting everything here. Everything I write on this is going to be projected. I'm recording it, and then at some point later today, I will push this out to YouTube. And so you could actually access everything I put up here, everything I say. I will send a link to Stephen that he can forward to you, okay? And while I'm saying that, if anyone wants to, if you look up on YouTube, Robert, that's me, Math Guy. If you do a search on YouTube, Robert Math Guy, I have all my classes for the past year or two have been done like this. And I've taught Cal 2 twice like this. So I have 2 semesters of videos that you can go back and, so if there's something integration by parts, something like that, that you want to just see a different perspective on, it's all out there. Okay, so it's public, feel free. All right, now I need your help to tell me what in the hell I'm doing today, because I've been told 6.2. Have you done anything out of 6.2? Nothing at all. Okay, so we're starting blank slate 6.2. All right. Now, normally I would answer questions over homework and things like that, but I'm going to let Stephen do that when he returns. I'm just here to provide information about Chapter 6, Section 2. And make sure I'm in the right place here. Trig integrals. I will also, when I'm up here writing, everything I write, I'll save to a PDF. Y'all know what a PDF is? And then I'll send it to Stephen, then he'll send it to you. And so you can print out all the notes that I wrote on the board later on also, if you don't want to have to watch the video. Okay, so 6.2. Trig integrals. Now, what have you learned up to this point? I mean, what type of integration have you learned? Integration by parts, right? So I'm not sure how much your instructor has told you. You know, there's several techniques we're trying to get, master. And integration by parts is the first important one. And now trig integrals are going to be just what you think. Integrals and techniques and how to attack integrals that involve trigonometric functions. So I'm going to start off with examples, all right, just to kind of get us going. So let's say we have an integral like this, sine squared x dx. So I want to find the antiderivative, right? The derivative of what gives me this, gives me that thing inside. What do we call that right there? Integrand. Y'all heard that before? Integrand. Okay, that's the integrand. Just like in a radical, the thing underneath we call the radicand. The thing inside of an integral is called the integrand. So what we want to do is find something that when we take the derivative of it, we get that integrand. So start thinking about integration by parts. Think about integration by parts. Would integration by parts work with something like this? Well, what have you been kind of told about integration by parts? Like, when do you use it? Or do you just kind of take a swing at it with it? Or how? I need your mental process here. Is there any process for integration by parts yet? Okay, so you maybe have like 2 functions next to each other or something like that. Let me put a comparison integral up here so you can kind of see the difference. Okay. What makes calculus 2, I think, the most challenging? I've been told this by my Cal 3 class even this semester, that what makes Cal 2 the most challenging of the calculus sequence is that there's all these techniques that you learn, and then when you see an integral, you don't know which technique to use. And it takes like hundreds and hundreds and hundreds of practice problems for you to just look at it and go, that's what I'm going to do. Right now you have integration by parts, so there's really, I mean, every problem you've seen is going to be integration by parts or basic substitution. As soon as we do trig integrals, now you have all these other things, and then next section, more and more and more and more, and by the time you get to an exam, you look at an integral and go, what do I use, right? So let's make a distinction between these two. When you do integration by parts, you have to choose one of your, let's say, factors, x here, to be something in the formula, and then the cosine x dx to be the other part. Yes? Are we on the same page there? Okay, you were told, hopefully, something like you choose one of them is u, the other one is dv. That sound familiar, right? Okay, now, in the formula for integration by parts, it was integral u dv equals uv minus integral v du. Is that the way you saw it? Okay. Were you told that little thing, little catchy thing to remember it? No. Okay. If you have if you're trying to do integral of u vd, then the answer is ultraviolet minus voodoo. Ultraviolet minus voodoo. It's just a cheesy way of remembering it. I'm not a real big fan of cheesy things, but I remembered it that way as a student, and if it helps you, then it helps you. Ultraviolet minus voodoo. So what's key here in the formula is that what happens to u in the new integral and what happens to dv in the new integral. Something very, very important happens. This integral, the u that you chose here, changes and becomes what? The derivative of it. And then over here, the dv, the part you chose for dv, changes and actually becomes the antiderivative. And so we call this transferring the derivative. In integration by parts, you're actually taking the integral that you don't like and transferring the derivative from one to the other. Does that kind of make sense? So I'm looking back up at this x cosine x dx, I look at this and I say, which one of these would I prefer to have as u? Because I know that when I go to my new integral, that whatever I choose for u is going to be its derivative over here. So which of those has a nice derivative? X, right? Derivative of x is 1. Now, if I choose that x to be my u, then dv, I'm going to have to be able to find its antiderivative when I go over there. So I say cosine x dx. Can I find the antiderivative of this by itself? Yes, right? Antiderivative cosine sine. So it makes perfect sense, hopefully, that if I choose my u to be x, my dv to be cosine x dx, when I transfer the derivatives, my new integral will be nice. Right? Okay. Using that same mentality, you look at this and you say, well, what's u and what's dv? Well, maybe you could do this. Rewrite it as sine x dx. You could. Right? Sine squared, sine times sine. Now, if I choose this to be my u, what's it going to be in integration by parts formula? What's it going to turn into over there if this is u? Sorry, I'm saying this. Let me just say, if this is u, and this right here is my dv, then when I do the transferring derivative, my sine x is going to become what in the new integral? Cosine x. And then I'm going to have to be able to take the antiderivative of sine x, which would become negative cosine x. So I'm going to have a cosine x times a negative cosine x, which will become cosine squared x. So I've changed the integral from a sine squared to a cosine squared. That doesn't help, does it? Do y'all see that? I mean, all it did was change it from sine squared to cosine squared. Other than that, then what do I do with that? So that seems to get, I guess, an empty path there, or dead end. Does that seem like that to you? So what can we do? Well, a lot of this section, at least the first part of it, is going to be about trig identities, things that you may or may not recall from pre-cal. So this is where pre-cal is going to come into play. I'm not sure what Mr. Gonzalez is going to allow you to have on a test as far as formula sheets, but everyone should have, at least in the back of their book, There's a reference page. If it hasn't been torn out, there's a reference page for trigonometry. It's reference page number 2. And there are a bunch of formulas in here. Okay? One of them is called the half angle formula or half angle identity. And here's what it says. It says that sine squared x is equal to 1 minus cosine 2x over 2, which is the same as 1/2 minus 1/2 cosine 2x. This is called the half angle formula. It's in the bottom right corner of this sheet. Has Mr. Gonzalez said anything about you being allowed to use formulas? Okay, so is he providing or do you have to provide? You're going to provide it, but are you restricted to just these out of the book or no? You don't know yet? Okay. As long as it's not worked out problems and stuff? Okay. So I would make sure I get my hands on all those trig things if you don't remember them. There's another one. While I'm here talking about it, there's another one for cosine squared x. And it's very similar. The only difference is a plus sign right there. Notice that in both formulas, either one, it's always going to be cosine in the answer, right, in the identity, and it's a double angle. So what happens is it's kind of like you're allowed to take a squared trig function here and drop the power down, but what the give and take here is that you wind up doubling the angle. So some people call this a power reducing formula. This book doesn't call it that, but some people call it power reducing because it reduces your power but doubles your angle. All right, got it? Now, if we use this formula for this integral, it becomes, I'm just going to replace the sine squared with 1/2 minus 1/2 cosine 2x dx. And now I'm in business. I'm going to check something. Yeah. Okay. If I could get a volunteer to just tear out a sheet of paper and put, to start a sign-in sheet, just pass, someone here want to do it? Go ahead. Just write your name legibly. Don't do fancy stuff, just so someone can read it. Yes, sir.
So why use half angle and not just regular identity?
Oh, great question. Great question. Let's address that. Let's see if I just jump real quick to a new page. If I were to take sine squared x dx, the Pythagorean identity that I could possibly use, I think that you're referencing is this one, right? Okay. So I could solve that identity over there for sine squared, and it would become 1 minus cosine squared, wouldn't it? So what would happen is I would have integral 1 minus cosine squared x dx. And you could look at that as two separate integrals, right, because you have subtraction between the two. The first one would be the antiderivative of 1. The other one would be the antiderivative cosine squared. But then that cosine squared, you're still back to kind of where you were with the sine squared, right? Like how do you attack that one? Do you see what I'm saying? So it's not wrong. This wouldn't be wrong, but you'd still have to figure out a way to get that cosine squared. What's your substitution going to be though? Right? Let me just look at that integral right there. Will u sub work there? Because if you do u sub, don't you need a u, and then don't you need its derivative to also be there somewhere? So if you use cosine x for your u, the derivative negative sine x dx has to appear there somewhere, and it's not there. See that? Yeah. Okay. Good question. All right, going back here. Now look at this integral. You have a constant, right? Subtraction. So you can split it into two integrals. And then you have a constant in front of a cosine function. That cosine function is not being squared now, right? So can we try and address that real quick then? Let me get to a new one. Couldn't I break that up? Integral 1/2 dx minus 1/2 integral cosine x not x, it was what? 2x dx. So I just separated in two integrals. How about the first integral? Antiderivative of 1/2 with respect to x. 1/2 x, right? The antiderivative of a constant with respect to x would be the constant in front of x. And then plus c, right? But what we'll do is we'll leave a c till the very end. Minus, now on this one, minus 1/2, can you do the antiderivative of cosine 2x? Yeah? What if it was just cosine x? Antiderivative would be sine, right? But if it's cosine 2x, the antiderivative is not just sine 2x. What is it? Close. If I said this, would that be right? What's the derivative of that? 2 cosine 2x, right? 2 cosine, because chain rule. Take derivative of sine of 2x is cosine 2x. Derivative of what's inside is 2. So you'd have 2 cosine 2x, wouldn't you? But we're going antiderivative. So we're trying to get from here back to here. We know that the derivative of this has a 2 sitting in front of it, doesn't it? We need to undo that 2. So we have to come in with the 1/2. Now let me do it this way, because I mean, this will probably help you a little more if I do it this way. What if you have integral cosine of any linear argument? In other words, if I have a cosine function and inside of it is a linear expression, the antiderivative of it will always be this, plus a constant. In other words, you have to scale it by whatever's in front of the x, you have to scale it by that number. You have to reduce it by its reciprocal. Take the derivative of this, what I just did in blue there. What's derivative of sine of ax plus b? Cosine of ax plus b times, what's derivative of ax plus b? Just a, right? Because a times x, the derivative is a. B is a constant, 0. So derivative of sine of ax plus b is cosine ax plus b times a. But then the 1 over a out in front of it, what does it do? Kills off that a that we had from chain rule. And so you just get the cosine ax plus b. This will always work for, this right here will always work for cosine or sine or tan, anything. You always scale it by 1 over a. So back when you do this problem, I hope this is making sense. The only reason I'm kind of skipping pretty quick through that is because that's basic substitution. That's another way you could get that one. So I'm going quickly through it, not really explaining it real well, because cosine 2x is kind of behind us at this point. So what I'll do is I'll look at that, integral cosine 2x. I know I have to scale it, so I have to do 1/2 in front to get rid of the 2, and then the antiderivative of cosine is sine. Sine 2x, and then plus c. And then put things together, I get negative 1/4 sine 2x plus c. Yeah, I hope that made sense. Are there any questions? Let's look at something a little more advanced than this. How about if I do sine to the 4th x dx? Well, you can throw integration by parts out. It's not going to work, right? Integration by parts. What we just did worked, but it was the formula we have is for sine squared, right? Not for sine to the 4th. But I could write this as sine squared x times sine squared x, couldn't I? Dx. Can I split that into 2 separate integrals? Can I do sine squared x dx times integral sine squared x dx. No, because you cannot split integrals up if there is multiplication between them. Only addition and subtraction. If we could do that, Cal 2 wouldn't be that hard, because you could always take things like this and just split it up in a bunch of integrals and then get the answers and multiply them all together. But that's not the way you undo the product rule or the quotient rule or the chain rule. You don't just split it apart. So unfortunately, life doesn't work out that way. So we can't do it that way. So instead, what I will do is each one of those I will write using my, what do y'all like, half angle identity? Not half angle. Is that what they call it here? I forget what the half angle formula. I always say power reducing. So if I say power reducing the rest of the class, are y'all going to be okay with that? I'm referring to the half angle on this. Okay. 1/2 minus 1/2 cosine 2x. The other one is 1/2. Same thing, right? So you see, I just replaced both of them. And now, guess what you get to do? Expand that out. Multiply it all out. So you have to do our good old friend FOIL. Not really a good friend, but 1/2 and 1/2 multiplied to be 1/4. 1/2, and then over here you get what? Negative 1/4 cosine 2x, and then the inners also give you the same thing, right? Negative 1/2 or negative 1/4 cosine 2x. What do the last ones multiply to be? What is it? Hello? I've done positive 1/4. Okay, good. Positive 1/4 cosine squared 2x dx. Now, the inside here, am I showing too much detail, or is this okay? I'm just doing it the way I would normally do it. So I can put those together, can't I? They're like terms. So put those together, it becomes a negative 1/2 cosine 2x. So I'm starting to feel pretty good about things here, because I have 1/4, I have minus 1/2 cosine 2x, and then I have plus 1/4 cosine squared 2x dx. Tell me about this integrand. Can I split it into 3 different integrals? Yes. Can you find the antiderivative of 1/4? Yes. Can you do the antiderivative of 1/2 cosine 2x? We just did that a little while ago, right? Can you find the antiderivative of cosine squared 2x? Not right away, but guess what we can use on it? The half angle identity again. Right? We can. And so that's what we'll do. So it kind of sucks, but, you know, I'll break it up into separate integrals. I go 1/4 dx minus integral, let me see, 1/2 integral cosine 2x dx plus 1/4 integral. Now let me highlight what I'm doing here. That one right there, what does that become? Half angle identity. 1/2 minus 1. Oh, cosine, sorry, it's my bad. We are doing cosine, not sine. Did I do it right earlier? Yeah, it was sine. Okay. I always remember if it's plus or minus, if it's sine, it's subtraction. S subtract, and cosine is just not subtraction. That's the way I remember it. I always remember the 1/2 and then something 1/2 cosine double the angle. But I always get the sine thing. I always have to have something to remember. I'm not big on memory. Usually math people aren't big memorizers. Usually, like your biology, you memorize a lot of things, but I was not a memorizer, so anything will help for me. Let's see, 1/2 plus 1/2, what though? Cosine, right? But we're doubling the angle. What was the angle here? It was 2x, right? So we have to double it. 4x. That's the tricky part there. Not only do you have to use that half angle identity twice, in that second application, when you double the angle, it becomes 4, not 2. Are there questions? 4x becomes the 2x there. Are there questions there? And then look at that integral over here on the right, the one that's yellow. Look at that one. Can you do what's in there now? Should be able to, right? 1/2, we can find the antiderivative of 1/2. And then over here is cosine 4x. See, it's not squared anymore, we're happy. So let me write the next line. I'm going to start integrating if I can. Antiderivative of 1/4 is 1/4 x minus, what did we say the antiderivative of cosine 2x was? Forget this right here. 1/2 sine 2x, right? But then I have a negative 1/2 in front of it. So negative 1/4 sine 2x. Is that all right? Plus, let me distribute that 1/4 through. I'm going to have integral 1/8 dx plus integral 1/8. Well, I'll put it in there. It doesn't matter. All I did there was distributed the 1/4 through in here. I could have taken the 1/2 out. I probably should have done that. It does not matter. It's just numbers, right? Just constants. Showing you different ways of doing it. Questions there? What's the antiderivative of 1/8? 1/8 x. So 1/4 x minus 1/4 sine 2x plus 1/8 x plus, drum roll, thank you, what is the antiderivative of, let's do the whole thing. What's the antiderivative of 1/8 cosine 4x? See if you picked up on that formula. 1/32 or 1/32 sine 4x. There you go. So it'll be 1/32 sine 4x. And then plus some constant of integration. And we're still not technically done. The book will go further because they'll combine like terms. 1/4 and 1/8 can be combined together, right? So what's 1/4 plus 1/8? 3/8 x minus 1/4 sine squared x plus 1/32 sine 4x plus c. We are there. Now, can you imagine what trying to integrate sine to the 8th x would be? Sine to the 8th. That's called torture. I mean, just did I go too quick? Do I need to keep that up? Okay. Back up there. Imagine sine to the 8th. I'll just squeeze it in over here. Sine to the 8th. I'm not going to do the whole problem. If I was trying to integrate that, I'd have to go sine squared, sine squared, sine squared, sine squared. Then each one of those would be power reducing or half angle formula. So I'd get 2 terms there, 2 terms there, 2 terms there, 2 terms there. And then I have to expand each one of them. And I'd wind up getting things like to the, I mean, it would be a mess. And then you'd probably have to do power reducing several times in that problem. And that problem right there is a notorious homework problem. As a Cal 2 student, everybody should bleed through that problem once, just to get good at keeping track of parentheses, of things going through integrals, constants, keeping track of it all. It's a great exercise, but it is, at the end of the day, torture, tedious, all right? Okay? I don't know what your homework assignment's going to be tonight. I don't think I have that freedom, but I would recommend you at least look at how bad that would be. Okay, moving on. Let's look at something slightly different. What if we go integral sine to the 5th x dx? See, now we have issues because the power reduce here only works for evens, doesn't it? Like you can always rewrite sine to the fourth is sine squared, sine squared. You can always write sine to the sixth is sine squared, sine squared, sine squared. But sine to the fifth, you can't really write it as, well, I guess you could, right? Kind of. What could you, how could you write that? Sine to the fourth times sine. But then, yeah, you would have, the power reducing wouldn't work there because you would actually, you could try for yourself. I don't want to do it. But if you try power reducing with this, you're going to wind up with sines that don't have 2x in the argument, and you're going to have cosines that do have 2x, and you can't work with those. I mean, not easily. It can be done. But check this out. With this one, watch this. Because it's an odd power, right? Odd power. I can rewrite that as sine, let's say to the fourth x, sine x, dx, right? And you know that sine, I'm talking about this one, sine x dx is the derivative of cosine, isn't it? It's a derivative of cosine. So if it was just sine there, I'd be happy. I could integrate. But if I had a cosine also, it would be great. Because then I could do a basic substitution. I could let my u be cosine, and then the derivative of that is practically there, isn't it? So can you rewrite sine to the fourth in terms of cosine? So going back to this formula, this is that formula, the all-important Pythagorean identity, right? That Pythagorean identity lets you solve for either sine squared or cosine squared. So let's solve it. Let's solve it for sine squared. You get sine squared x equals 1 minus cosine squared x, right? So everywhere I see a sine squared, I can replace it with what? 1 minus cosine squared x. So let me try and massage this integral to make it look the way I want it to look. I'm going to write that as sine squared x in parentheses squared, then sine x dx. So I'm just rewriting sine to the fourth as this. Do you all agree that's the same as sine to the fourth? Okay. And what did we say sine squared x was? 1 minus cosine squared x sine x dx. I forgot my x. Bless you. I forgot to ask, is it too dark? Can you all see your own writing? Is it? It's always a balance trying to find enough light that you can see this. Now, I can't do u substitution yet. Well, can I? I mean, think about it. If u was this right here, cosine x, not squared, cosine, the derivative of cosine is negative sine. So we're off a little bit by sine, and that's okay? Maybe it would work. Do you want to try it? Or do you want me to go a little further? I mean, okay, let's just try real quick. I'm doing a u substitution, which was really the first type of integration you learned, right? Integration by parts is the first major technique, but before that, u substitution was there. So I'm going to let u be what? Just cosine x? Okay, why not sine? Okay. Okay, but I have, if u is sine, the derivative cosine is right, I mean, derivative sine is cosine is right there. That's okay. So what's wrong with it being there? If u is going to be sine, the derivative of it, you do not want it to be trapped inside of a big, ugly expression. You want the derivative of it to be just sitting there, just right there by itself, and outside of all the complication. You understand what I'm saying? If you let u be cosine, that part's in the complicated expression. The derivative of that, even though I'm off by sine, is sitting right here, sine x dx, just waiting to be integrated. Make sense? You're in the right place, I'm pretty sure. Does he look familiar? Okay. You're in the right place. So Let's try it. Okay, if u is cosine x, are you learning it this way? Du is negative sine x dx? Is that the way you write it? Or do you do du dx equals negative sine x? Just like that? Okay, now what? What do you do now? I'm asking you because I need to show it to you the way that I guess makes sense to you and the way you've been shown, because there's many ways to approach this.
Now it would be integral of 1 minus u squared du.
Okay, is sine x dx out there, is this this? Not exactly, it's off by a sign, right? How do you take care of that? I guess what I'm getting at is I'm trying to figure out how it was shown. Let me just tell you the way I would tell a class, okay? What I'm trying to do is I'm trying to get the thing that appears here, I'm trying to get it to match exactly what's in my integral. So I'm trying to get this to match. So the only way I can get this sine x dx right here is if the negative in front is not there. So all I do is I multiply both sides of this equation by -1. So I go negative du equals sine x dx. And now this yellow right here matches exactly the yellow up there. So I will replace that yellow with what? Negative du. So for me, it's always a match game. I match and plug in. Yes? You can pull the negative. Well, pull the negative out of where? Okay. But there is no negative out. There is no negative up there. Okay. If I replace this right here, see, I'm trying to figure out how you're. I think I understand what you're saying, but I'm trying to think of how that could potentially be dangerous too. If you're happy with this and you're comfortable with it, I'm not here to make it complicated. I'm just, if you're still kind of hung up on this, I'm just showing you the way that I would do it. I get the derivative. I take this, whatever my u is, I take its derivative. I say, do I have that up there? No, I want that. I'm almost there. Just got to get rid of this negative, multiply both sides by -1. I'm there. This gets replaced by this, period, end of story. Now, when I put negative du up there, I will draw the negative out. But that'll be after I write it down. Okay? So now what I'm going to do is rewrite the integral. So I don't put equals, I put an arrow, because this is not equal. We made a substitution. So it's 1 minus what? U squared. And then what's sine x dx going to turn into? Negative du. Now I pull that negative out. Integral 1 minus u squared du. And that is just a polynomial in u, isn't it? What would be the best way to try and integrate that? Thought I heard it. Just expand it out, right? Multiply the whole thing out. That's going to be, in case you don't know what I'm saying, squaring means to multiply it times itself twice, right? So I'm going to get integral 1 minus 2u squared plus u to the 4th du. And now can you find the antiderivative of all those? You comfortable with that? What's the antiderivative of 1? Be careful. What's your variable here? What's your integration with respect to? The antiderivative of 1 with respect to u is u. But I have a negative out front, right? So I'm going to make it negative u. What's the antiderivative of u squared? 1/3 u cubed. But then you have a -2 in front of it, but then you have a negative in front of that. So 2/3 u cubed plus 2/3 u cubed. And what's the antiderivative of u to the fourth? 1/5 u to the fifth, but then you have a negative out front. So negative 1/5 u to the fifth plus a constant. Is that the answer? I boxed that or what?
No, it's not all about you.
I haven't heard it put that way. That's kind of cute. What's that?
From our inspector, it's not original.
Oh no, I know that. I could tell. I could tell the way everyone laughed. You were just waiting to like fire that out. Okay. So all right, the u is cosine, right? Wasn't it way back up? Yeah. So negative cosine x plus 2/3 cosine x cubed minus 1/5 cosine x to the fifth plus c. And we're in business. We're done. You could also write those cosines, these right here, as cosine with the little 3 there, right? And you could do cosine with the 5 here. Either way. I mix it up a little bit because I like everyone to remember that they mean the same thing. All right, so are there any questions on that one? What do y'all think? Well, that would go back to how you were taught u substitution. So the first way that you ever, at least again, this I can only speak for the way I do it, and that's the thing about Cal 2. Everyone kind of approaches it slightly different. All right. When you are going to use substitution, u substitution, then what you're trying to do is you're trying to see if you can find something, and its derivative is sitting there too. Now that works most of the time, but sometimes it actually, u substitution works even when you don't have that. But those are the more complicated problems. But in general, you know, if I have something like this, automatically that's u substitution to me. Because I see something, and I see a scalar multiple of its derivative. So if I call x cubed u, its derivative, x squared, well, off by a constant, right, is there. So I guess to answer your question, the pattern that I would be as a student looking for u substitution is, do I see something, and do I see its derivative or a multiple of its derivative? If so, take a swing at it. And you always want its derivative, right, the derivative x cubed, you always want that to be sitting next to your dx or du or whatever, it's all on the same line. You don't want it to be down the denominator. You don't want it to be trapped underneath a root, because that part right here is going to be replaced with du, isn't it? So you can't have that stuck under a root. It's got to be able to be slid to the side and the back of the integral. Does that make sense? Okay. Okay, let's look at another one. Cosine to the 7th x dx. I'm not going to work through this whole problem, all right? I'm just going to show you how to set it up. The thing is, you look at it, you say odd power on cosine, right? If it was even power, you start thinking power reducing formula. That's what you start, the half angle out of the formula, that's what you start thinking with even powers with sine and cosine. When you have odd powers of cosine and sine, you start thinking, I'm going to peel one of them off and then work with the other one and try and use Pythagorean identity. So I would write this as cosine squared x to the 3rd cosine x dx. So I kind of did 2 steps in one there. I peeled one cosine off to the side, which would have left me with a cosine to the 6th, right? But I rewrote cosine to the 6th as cosine squared to the 3rd. And now I can replace cosine squared with what? 1 minus sine squared x cubed cosine x dx. Do you see that that's pretty much the same problem we just did a second ago? Except we had cosine in here and sine out here, didn't we? Now we have sine inside and cosine. This is real nice because what's the derivative of sine x? Cosine x dx. So we're even better off. We don't even have that negative to worry about. So I'm going to stop here, but I'll show you what you would do the substitution of. U is sine x, du is cosine x dx, and you're off to the races with that. Do you see where this is going to be a little bit messy? When you replace the sign with u, right? You're going to have 1 minus u squared cubed. And then you have to expand that out. So you have to do 1 minus u squared times 1 minus u squared times 1 minus u squared. So you're going to have 6 terms. Dot, 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 dot. Oh, the dot, dot, dot means that's for you. Next one. How would you do that? Well, I need the dx on the end, but how would you do that? You see that and you think power reduce. But then I do this. Okay, follow me through this, please. Because that cosine was odd, right? Cosine cubed, I could peel the cosine off of that and take it out to the outside, and that would leave me with cosine squared, wouldn't it? Then the cosine squared I could use Pythagorean identity on to make it a 1 minus sine squared, right? Now I still have the sine to the fourth out front. Yeah, right now, do you see that you have u du? If your u is sine x, then the derivative of that would be what? Cosine x dx. So this would be replaced, and you would become what? I'm going to do the switch here. U is sine x, du is cosine x dx. This matches with this exactly, so I'm going to replace the yellow with du, and I'm going to replace all my signs with u's. So it's u to the fourth, 1 minus u squared du. Y'all see that? Or? And then how do you integrate this? Just distribute u to the fourth through. U to the fourth minus u to the what? Sixth du. That's 1/5 u to the fifth minus 1/7 u to the seventh plus a constant of integration. And then you replace all your u's with sine x. So the final answer would be 1/5 sine to the fifth x minus 1/7 sine to the seventh x plus a constant. Do you see how that works? Feel okay with that? Questions? So what if you had something like this? We just did, what if we had sine to even x, cosine to odd x dx? That makes sense? That's what we just had, didn't we? All we did was, since cosine was odd, we peeled one of them off, right? Which made cosine, what was left, cosine and even. Then we used Pythagorean identity, and we put those two together, and we were able to work it out. And that will work for sine and cosine if one of them is even and one of them is odd. And it could have been the other way around. The sine could have been odd, and the cosine could have been even. And we could have done the same sort of thing. Whichever one is odd, you peel one off. Now, the book does have some kind of, I don't know, it's helpful hints. What chapter are we in here? 5.3? No, wait. 6.3? 6.2. Okay. 6.2, which is on page 317, in the margins of the book, okay, right in here, they have little hints, things that you can try. Like this one says, how to integrate powers of sine and cosine. If the power of cosine is odd, save one cosine factor and use cosine squared equals 1 minus sine squared and express the remaining terms and factors in terms of x, then substitute u as sine x. That's basically saying what I'm saying here. Peel off the cosine, rewrite the cosine using Pythagorean identity, and so on and so forth. So I'm just pointing out in the book it does have some of this written down. And then on the next page it has how to integrate other things, and then it keeps going, okay? So just, you can point to that if you want some helpful hints. I'm not going to go any further with that. How about if you had cosine squared x sine squared x dx? Now they're both even, right? So you can't peel one off. But what did we do with those? The power reduce or the half angle? Is that what you're, yeah. Okay, so I could change the first one to be 1/2 plus 1/2 cosine 2x. I could replace the second one to be what? 1/2 plus 1/2. I don't know why I keep doing that. Minus cosine 2x dx. And then if I distribute through, I get integral 1/4. What happens on the inside? Do they cancel each other out? 1/2 and 1/2 is 1/4. 1/2 and negative 1/2 cosine 2x is negative 1/4 cosine 2x. The inside is 1/2, 1/2, so it's 1/4 cosine 2x. The middle ones go away, don't they? So when I get the last ones multiplied to be minus 1/4 cosine squared 2x dx. And now, can you integrate the first term of that integral? Yes? Over here? What? Use the half angle. The same thing, the power reduce again. So that one right here, the cosine squared 2x, we would have to do half angle again on that one. And then you carry it on the rest of the way. Do you understand that? Are there questions on that? Dot, 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 dot. I'm getting some looks of like, I'm not sure if that means I'm killing you, boring you to death, or if you're okay with that. What would, when you use the half angle though, what would you get in there? Cosine what? 4x. Just remember you're going to double 2x, so you'd get that 4x in there. All right. Moving along. Is pace okay for you? I say that as if you have a choice. Yes. 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 If you would have changed that, it would have been 1 minus sine squared x, right? Then you would have had the sine squared x already. Then we distribute through, you get sine squared x minus sine to the 4th x dx, right? All that integral, whatever. Then what you would have to do is you have to power reduce the first one. The second one would be sine to the 4th, so you have sine squared, so you have to do power reduce on both of those, multiply them together, which would require another power reduce in that one. And eventually, yes, it would work out. But I think that would be a little more work. But it's not wrong. Okay? Yay. So now we're going to look at some of the other trig functions. So far we've done sine, cosine, but we have not messed with anything else. Let's talk about tangent and secant. Now, a couple of things to remember before we begin. What's the derivative of tangent? Secant squared x. What is the derivative of secant? Careful. Secant x tangent x. And what is the Pythagorean identity that involves tangent and secant? 1 plus tangent squared x equals secant squared x. Those are the things we're going to need as we proceed. Just remember, derivative of tangent x is secant squared x. Derivative of secant x is secant x tangent x. And the Pythagorean identity that relates tangent and secant together is 1 plus tangent squared x equals secant squared x. If we remember that, then we should be able to go with this. Let's start, though, with, kind of go through the process, the mental process in this problem. What would you do? So right now, again, we have basically three things: basic substitution, integration by parts, and now trig substitution. Or sorry, no, trig integrals where we're using formulas, right? Okay, so you're seeing that you see tangent's derivative there, right? Secant squared is the derivative of tangent, isn't it? So don't I have something? Forget the square. Don't I have just tangent? Don't I have tangent and its derivative right next to it? That means if I call u tangent, then there's its derivative. So if u is tangent x, the derivative of that is secant squared x dx. And I can rewrite the integral how? What's tangent for us? U, and it's squared, right? So u squared. And then what's that whole blue thing? It's exactly du. And the antiderivative of u squared is 1/3 u cubed plus c. But what's u? What is u? Tangent x. All right. How about this? Integral tangent cubed x secant cubed x dx. What's different here? The cubed, right? If it was squared, this would be the same problem. Okay. I think I'm I you know what? That was your instinct, right? That's actually right, but let's see why, okay? The last time we let u be tangent, right? And the derivative of tangent was right there, secant squared. Okay, in this one, what we're going to have to see is this. If we peel off, remember we were peeling off things earlier? If we peel off one tangent and one secant and just write it to the side, then that's what we would have, right? And we know that secant x tangent x dx is the derivative of what? Secant, which I have secant here, but I also have tangent. It'd be really nice if that tangent was secant, right? But what is tangent squared x? Go back to your Pythagorean identity. The identity we have is 1 plus tan squared x equals secant squared x, right? That means that tangent squared x is equal to secant squared x minus 1, isn't it? So I can rewrite this tangent squared x, I can rewrite it as secant squared x minus 1. And then I still have that secant squared x next to it. Then I still have that secant x tangent x dx. Now you can let your u be what? Secant x, right? If your u is secant x, the derivative of it's right here, and you'll be able to rewrite the whole integral in terms of u in du. Well, secant, because what's the derivative of secant? Secant x tangent x, right? So that's why I choose it. So u here would be secant x. Du would be secant x tangent x dx. And that means that those blues match up. Integral would become u squared minus 1 u squared exactly du. And then distribute the u squared through. Power rule on each term. You're done. I think it's going to be 1/5 secant to the 5th x minus 1/3 secant cubed x plus a constant. Anyone agree? No? No one agrees? That all right? Okay. And what's the good news with integrals? I mean, you can always check your answer, right? We don't usually do it, but you can check it by differentiating it. All right. Well, that is all I'm going to show you in terms of what's called trig integrals. Those are integrals where your integrand has sines and cosines and tangents and secants. You definitely have to go through this homework, because just watching me do this is not enough. You have to go, I mean, I'm sure you probably know this, hopefully by now. You have to do your homework to get good at this, right? So I will let Stephen assign the homework. Yes. Yeah. I don't know. That's kind of why I'm here a little bit. I'm trying to hope to get people who want to take Cal 3 in the summer that might want to do it. So, Di Giovanni is my last name. Yeah. Robert D. Giovanni. Yeah. Sorry, I didn't introduce myself, did I? Oops, sorry. I did? Okay. All right. You may have heard horror stories about me, so I'll be straight up. I'm not the easiest instructor, so just FYI. I mean, it's not. This is the way I do class. Yep. You can go watch my YouTube video. I mean, of my Cal 2. All of these videos, like what I'm doing right now, I'm recording this, right? This will all be up later. And if you want, you can go watch my old Cal 2 classes, and you can see that's what I do. This is it. So, okay. Some of my older Cal 2 stuff, I used to actually bring a camera, and I'd be on the board, but it was too much stuff. I mean, not like this isn't too much stuff, but this is a lot better, right? Like I can just move around the room, and I'm not tethered to anything, and I don't have to follow myself with a camera. So, whatever. Yeah. Hire a cameraman, exactly. Big universities, that's what they do. They have student aides, and the professors will get up there, and they've got someone dedicated to filming them. But not here. So I got to film myself somehow. All right, let's move on because this section is cut up into two pieces. The first part is trig integrals. The second part is trig substitution. In all honesty, I would never try and cover this in one day, and I don't know if that's what your instructor wanted me to do. I'm not going to attempt it. I'm just going to go as far as I can, all right? Because that first part right there, that's a couple hours of homework worth of stuff right there. This next topic in the same section is another couple of hours of homework. And it's a totally different idea. So let's just see how things go here, all right? So let's start with this. This is called trig substitution. Trig substitution. What we were just doing was called trig integrals. Trig integrals. This is trig substitution. This means we're going to be doing integrals, we're going to be making a substitution, and somehow it's going to involve trigonometry. So let's start with something that's going to seem very, very, very strange to you. Just see if you follow me. Let's say I just write this down. X equals A sine theta. Okay? I just wrote that equation down, all right? Everyone, X is equal to A sine theta. Now, do you agree with this? X is equal to, X over A is sine theta. Is that true? As long as what? A is not 0, right? So we could put a little like asterisk here, if A is not 0, because of course if A is 0, then you can't divide by 0. But I mean, we don't normally need to say that, but I'll just point it out. So that's true. Now, back from pre-cal, do you remember that when you're learning about right triangles, that if you call the angle inside theta, and you have these sides of the triangles, that sine was a certain side over a certain side? What was it? Opposite over hypotenuse, right? So just a quick poll, how many of you use the SOHCAHTOA? Ooh, a lot of you, SOHCAHTOA. So if you've never heard SOHCAHTOA, it's this Indian, Native American Indian girl. Her name was SOHCAHTOA. She's really good at math. Right? Is that the story you heard too? SOHCAHTOA. There are people here who haven't heard of her. So her name was SOHCAHTOA. Is excellent at geometry. And it just so happened that her name, SOHCAHTOA, matches the fact that what? Sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So it just worked out beautifully. Right? That's a way to remember those, right? SOHCAHTOA. So opposite over hypotenuse. So do you agree if I work off of this equation and I try and match a triangle to that equation, my triangle would look like this? X there and A there. Do you agree that that triangle matches this equation? Yes? And if I have two sides of a right triangle, can't I always solve for the third side? How would you solve for that base of this right triangle here? It would be square root of A squared minus x squared. Other way around, yeah. That's what it would be. Now, I'm going to highlight that one because that's the one you would have to solve for. And you could do it using the Pythagorean identity that whatever this squared is plus this squared is this squared. And then you could solve for that unknown side. If you do that, you would get root a squared minus x squared. Uh-huh. Oh, law of sines. Yeah. Yes. But that's not with this. We're not applying that here. Yeah. That goes for any triangle. It doesn't have to be right. So with this triangle I drew related to this equation here is what we call a reference triangle. It's a visual way of representing this equation. Do you all agree? I think one of the biggest things coming out of this, what we're about to do, is your ability to create reference triangles. So any questions on that? No? Okay, let me try and see if you can create a reference triangle for this. What if I start you out by saying x is equal to a tangent theta? Can you get me a reference triangle off of that? So let's try the same thing. Divide both sides by a again. You get tangent theta, right? Draw a reference triangle. Please realize that the triangle that you're drawing now has nothing to do with the triangle we just drew, right? Totally different problem. Different equation, right? Different triangle. So what would it be? What about my hypotenuse? What's my, well, no, the hypotenuse is the harder part. What's my opposite side? X. What's my adjacent? A. Then what's the hypotenuse? A squared plus x squared, but then square root. Don't forget square root. Could you do that? I want you to do one more, and once we do that, we'll be ready. We will be armed with what we need to attack these integrals. All right, x equals a secant theta. Divide by a. Reference triangle. What is secant? It's the reciprocal of cosine, isn't it? So instead of opposite over hypotenuse, it's hypotenuse over opposite. So how should this look? My hypotenuse is what? X? Wait a minute. Hold on. What did I say? Secant is the reciprocal of what? Cosine. Cosine is adjacent, right? SOHCAHTOA. Where is she? Okay. Ka. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Didn't I say hypotenuse over opposite? Didn't I say that? Okay. Sorry. So x is the hypotenuse, though, right? And then I need adjacent to be a, and then the opposite is root x squared minus a squared. Right? Any questions? Those are the only three you're going to need to be able to do. But check this out. I'm going to point something out. It's really, really important here. In all three of these reference triangles, one of the sides of the triangle had a square root, right, with an x squared and a constant squared, a. Agreed? In the very first one, it was the constant squared minus the variable squared. In the last one, it was the variable squared minus the constant squared. And in the middle, it was addition between the two, right? Keep that in mind. That in each of these cases, we had one of those three situations come up. You ready to see what we can do now? It's going to be pretty exciting. I think you're going to like it. Let me see what I did in my class last time. I just brought in my notes from last time, and I guess I didn't. Oh, here we go. There we go. 1 over the square root of x squared plus 1 dx. I need a drink real quick, some water. Not that kind of drink. I mean, I do, but I'm not going to have one right now. Think about that for a second. Think about basic substitution. Think about integration by parts. Think about what we did earlier. Okay, I'd like to try and get one of these worked out. So let's do this. Basic substitution is not going to work. Integration by parts is not going to work. And then it's not a cosine or a sine, so none of what we just did is going to work. So we're kind of stuck. Now maybe there's some table in the back of the book that might have a formula for this, but we're gonna act like we don't know that the formula exists. And what I'm going to do is I'm going to recognize that this right here has the form of square root variable squared plus constant squared. Do you see that? Variable squared plus constant squared. Now go back to your 3 triangles. Which of those had variable squared minus constant squared? Was it the secant one? Yes? Variable squared minus, was it minus? What are we doing? Plus, sorry, plus. So which one is it? Tangent. But it's actually, remember, addition doesn't matter, right? You could flip x squared and a squared around here. So it actually looks like the tangent one, doesn't it? So what we're going to do is use this tangent one, go back to the problem. Now I know I'm thinking tangent, right? And I say, I'm going to make a substitution. And here is the substitution. It's x equals, well, what was it? Look back in, it was a tangent theta. But what's a for us in this problem? 1, because if that's a squared, what's the square root of 1? It's 1. What if that had been x squared plus 4? What would a be? 2. What if it was x squared plus 9? 3. What if it was x squared plus 2? Square root of 2. Doesn't have to be a perfect square, but you have to pay attention to it. All right? So I'm going to make the substitution x is equal to 1. I'll put it there even though I don't need it. 1 tangent theta. Right? Now, if I'm going to make a substitution, x is equal to 1 tangent theta, that means I'm going to replace all my x's with 1 tangent theta. Okay? What is the derivative of x then? What's dx? Well, what's the derivative of tangent theta with respect to theta? Secant squared theta d theta. Do you agree with that? Well, no, I'm saying taking derivative both sides here. So derivative of x is dx. Just like when we made u substitution, it was u and then du. Same thing here, but I'm doing x dx. Over here, tangent, instead of like tangent x, instead of having a dx here, I'm having d theta. Y'all agree with that? Now, what is the square root of x squared plus 1? Now, I'm taking that from this right here. That's what appears in my problem, doesn't it? What is it? Let's talk about it. It's square root of, well, what's x for us? Tangent theta. And what would happen if I square it? I would get tangent squared theta plus 1, right? So this is tangent squared theta plus 1. But what does the Pythagorean identity tell us tangent squared theta plus 1 would be? Secant squared theta, wouldn't it? And what is the square root of secant squared theta? Secant theta. Do y'all see that? Any questions? Are you ready to rewrite the integral? I am. Let's rewrite the integral. We would have integral 1 over, what was the square root of all that junk? What was the square root of x squared plus 1? That all turns out to be secant theta, right? Secant theta. And then, what? Don't forget this one. What is dx? Secant squared theta. So right here, next to this, I need to write secant squared theta d theta. Do you all follow what's happening here? Now, that's just integral secant theta, isn't it? D theta. And that is a basic formula. You should have this in your formulas, the antiderivative of secant. It's formula number 10 on your basic formulas. Oh, wait, no, not 10. Sorry, 14. Did you all talk about this ever? Natural log secant theta plus tangent theta plus c. I'm going to put a little 14 next to this. 14, that was formula 14. Are we done? No, this is not about theta. No, I'm just kidding. It's not all about that. See, it's not funny that way, is it? Maybe it wasn't. All right. So I need to switch everything back in terms of what? X. So you got to tell me now what's secant theta and what's tangent theta. This is where the reference triangle comes in. Let's go back up to where we had this. Do you remember where we put this right here? X is 1 tangent theta. That really means that tangent theta was x, right? Or x over 1. And that means if I draw a reference triangle, if theta's on the inside, it's opposite over adjacent. It's x over 1, which forces my hypotenuse to be x squared plus 1. Right? So that's my reference triangle. Now, if I can draw a reference triangle, I can tell you any trig function off of that, can I? What's sine of theta? X over that, right? What's cosine theta? 1 over that. What's tangent theta? X over 1. What's secant theta? Reciprocal of cosine, right? Cosine's 1 over this, right? So secant's that over this. With me? So the reference triangle allows you to get any trig function off of your triangle. So let's come back here and let's rewrite our answer. This is equal to natural log. What did we say secant theta just was? Go off your reference triangle. Square root x squared plus 1. Plus, what was tangent theta? Reference triangle. Tangent theta. X. X over 1. X. Plus c. Done. Everything's back in terms of x now. I have time for one more. Y'all up for it? One more. What's going to happen with these trig substitutions? Most of the time is that the integral that you're going to get, like you saw we got this integral, I'm going to highlight in this like big pinkish color. See that integral? That integral is a trig integral, which is what we started with today, right? It just so happened to turn out to be secant. But in a lot of these problems, it'll turn out to be, I don't know, cosine squared theta, sine squared theta. And then you have to do everything we did earlier on that, which might be power reducing formula and all that crap. And then once you get to that answer, go to your reference triangle and replace all your trig functions. So these problems can become a nightmare. On a test in a Cal 2 class I wouldn't never give you a question like we did earlier to start the class, like sine squared, all that. I would just give you a good trig integral, a trig substitution problem that requires that later. You know what I'm saying? Let's see if this next one gets interesting. I don't really care for that one. This one's kind of cool. All right, let's try it. No, I think that's too much. Hold on. I'm trying to keep it that you're still within the realm of sanity here. Integral 1 over x squared square root x squared plus 4 dx. I'm almost out of time. I don't know if I can get through this whole thing. So first, it's not basic substitution. It's not integration by parts. It's not a trig integral. So I start thinking, as soon as I see the square root and I see this stuff underneath it like that, I automatically start thinking trig substitution or trig sub. That's a lot of times we call it trig sub. And because I see variable squared plus constant squared, I start thinking a tangent theta, just like we did before. Now today I'm not going to do anything, any of the other examples where you would do a sine theta or a secant theta. I'll let Mr. Gonzalez do one of those next time, or a couple of those. So right now, I start thinking that I'm gonna have square root x squared plus a squared. I'm thinking a is what here? 2. If I do that, I can start by my substitution being x is equal to 2 tangent theta. Then I take derivative, 2 secant squared theta d theta. And what does the square root of x squared plus 4 become? You've got to be a little careful with this one. What's x squared? For us here, what's x squared? 2 tan theta squared, so it becomes 4 tan squared theta plus 4, right? X squared is 4 tan squared theta plus 4. And now, what the heck is that? Did y'all hear that? Okay, it's not just me though, right? Okay, all right. So here we pull a 4 out, right? We can factor a 4 out of each of these terms, and then we can actually pull it out of the root because square root of 4 is 2. So I can pull it out as a 2, and then underneath I have my tan squared theta plus 1, but that's just secant squared theta. So 2 square root secant squared theta, that's just 2 secant theta. Looking back up at this integral, I'm going to be able to rewrite this yellow right here as what? 2 secant theta, right? I'm going to be able to rewrite the dx as what? 2 secant squared theta d theta. But what about x squared? Well, we can square both sides of that, right? We did a little while ago. So that's just 4 tangent squared theta, isn't it? Okay, so let's rewrite the entire integral now. We shall have integral 1 over, we said this, the x squared would be 4 tan squared theta. We said that the square root would just turn into 2 secant theta. And we said that the dx sitting out at the end would become a 2 secant squared theta d theta. Questions? 2's cancel. One of my secants cancels. And I have a 4 on the bottom, which I will pull out as a 1/4 in front of the integral. I have a secant theta on top. I have a tan squared theta on the bottom, d theta. Do you all agree with that? Questions? Now, this is a little challenging. I mean, you look at it and you say, you know what? Let me get everything in terms of sine and cosine, because sometimes it's easier to work with things if they're in sine and cosine. So what is secant? 1 over cosine. And what is tangent? Sine over cosine. So that's sine squared theta over cosine squared theta. Then I have my d theta sitting out the side. See what I'm doing? Secant theta on top, tangent squared theta on the bottom. And then isn't a fraction over a fraction just reciprocal? Just bring it up, flip it. What would happen if I flipped that up there? What would you be left with? You get some cancellation, don't you? One of the cosines cancels. So I have a cosine on top. And what's still on the bottom? Sine squared theta, d theta. Now, looking at that, do you see the basic substitution? Let u be sine theta. What's the derivative of u? Cosine theta d theta. Do you have cosine theta d theta? Right there. And so you could rewrite that integral as integral what? Du over, well, 1/4 out front. Du over u squared? Du over u squared. Is that not the same as u to the -2 du? And what kind of rule would you use on that to find the antiderivative? Power rule? Yay or nay? No? Okay. Integral x to the n dx is equal to 1 over n plus 1, x to the n plus 1, plus a constant, as long as n is not -1. That's the power rule for integration. Well, this is like x to the n. N's not -1, so we're good to go. So we just do my little power rule, and you get what? 1/4, and then times -1 u to the -1. Damn it, I'm running out of time. Which is really 1 over 4u, isn't it? 1 over 4u? Or, yeah, -1 over 4u. I have to go to a new page. Ready? So I have that we're equal to -1 over 4u plus a constant. Now, what was u? So 1 over 4 sine theta plus a constant. What was sine theta? Reference triangle. What was, go to your reference, did we do reference triangle? We did do one? I never drew it, did I? I never did it. Do we have sine theta anywhere? No. You see what I need to get now? I need to get sine theta. So I have to go to my reference triangle. A lot of times I draw my reference triangle right off the top because I know I'm going to need it later. Here's theta. I know tangent theta is x over 2, which means this side is x squared plus, I'm moving fast because we're almost out of time. And we've done that already. So I divided both sides by 2. Tangent was based off that. So what's sine? X over yeah, square root of x squared plus 4. Got to jump back to my page. So this is x over the square root of x squared plus 4. But then I can reciprocal that back up, right? Flip it, because it's a fraction, and get negative square root of x squared plus 4 over 4x plus a constant. Done. Now we're starting to do some integration, all right? All right, well, I have to stop because I don't know, I don't have time for anything else. Like I said, I will email Mr. Gonzalez and let him know that I recorded this lecture.